Congratulations, you have just won a small lottery. It will pay you either five annual payments of 15,000 each, with the first payment to be received 2 years from today, or a single lump sum to be received today. If you can invest at a 6% annual rate of interest, what is the least you should accept as a lump sum pay amount? So here we can see that these annual payments represent an annuity. They represent an annuity. There are two types of annuities. Okay, there's an ordinary annuity and annuity due. Ordinary annuities are paid at the end of the period. Okay, so if a question is silent about which type of annuity, always assume ordinary annuity. Okay, annuity due is paid at the beginning of the period. Okay, so whenever you're dealing with annuity dues, you always put the ordinary annuity formula, but you multiply it by this growth factor, 1 plus R. Okay. So in this question here, we've seen that this 5,000 annual payments represent an annuity. Okay. So we have to find, basically, they're just asking us, and they're asking what is the least amount. They're just asking what is the present value of this ordinary annuity. Now, there is a twist also, because they've told you the first payment is to be received 2 years from today. So this represents a deferred annuity. Okay, a deferred annuity just means um, you won't be paid. Your payments will be delayed, basically like that. A payment will be delayed. Okay, like in this here, your first payment will be made by received 2 years from today. It means year one you're not going to be paid. You're only going to be your payments will start in year two. Okay. Yeah. So with a deferred annuity, some years you won't be paid. Okay. Oh, let me not put it like that. You won't be paid. Your payment is going to be delayed to be pushed on to another year. Yes. So here, as I said, it's a deferred annuity. Okay. Since you receive the first payment in year two, 2 years from today. So in year two, that's when you're receiving the first payment. So the deferred period is 1 year. Okay. So this is the formula for the present value of an ordinary annuity first here. CF just represents the cash flow, the equal payments, multiplied by 1 minus 1 plus the discount rate raised to the power negative n over r. Then when you're dealing with a deferred annuity, you're going to add this here. 1 over 1 plus the discount rate raised to the power d. Okay, d represents the deferred years. Okay, yes. So the cash flow is 15,000. Our discount rate will be this 6%, which is the annual interest rate. Okay. Number of years, 5. The deferral period, 1. Okay. So we can break this formula down. We can first find this yellow part. We solve this, and then we also solve the deferred part. Then we multiply them. Okay. Congratulations, you have just won a small lottery. It will pay you either five annual payments of 15,000 each, with the first payment to be received. Yes, yes, yes. There's a yeah. If there is no delayment, a defer, don't need to add this part, this blue part there. Okay, so we do our calculations here. Okay, start with the it's not 6 years. Uh. You have got it wrong there. It's not 6 years. It's 5 years. But you start receiving your payments in year two. Mhm. So meaning there's a delayment of 1 year, right? That's the deferred period. That's the D. D equals what? The deferral period, 1 year. Um, so when we do our tabulations, let me put them together here. All right. Since the deferred period is to the power one, so you just say 1.06 to the power one, which will just give you the same 1.06. So now this formula, this is where you have to be careful, okay? Because you have to do this in parts, okay? So as you can see here, we're going to start this. We're going to start with this part I've shaded here. We say 1 plus 0.06, 1.06. Okay, 1.06 to the power negative 5. Okay. Then you're going to say 1.06 to the power negative 5, you get 0.747258. Okay. Mhm. Then you're going to say 1 minus 1 minus 0.747258. You're going to get 0.252742. Okay. Then you say 0.25742 divided by 0.06, you get 4.217. Okay. So you start with this is called the annuity factor. Then you solve it first. Then 0.2527 divided by 0.06, 4.212. Okay, 4.212. Okay. Then you're going to say 15,000 times 4.212 times 0.94396. You're going to get 59,608. I've just put the whole calculation together here. Okay. 8,608.74. Any questions? Okay. You want to have exactly 8,000 in your account at the end of 5 years. The account allows you to make one deposit at the beginning of each year, right? At an interest rate of 9%. In order to have exactly 8,000 at the end of year 5, how much must you deposit each year? Okay. So here again, we're dealing with the question of annuities. Okay. Now, you have seen here, you have said at the beginning. Means this is a annuity due. Yes, it's an annuity due. Now here they've already told us what our future value is. It's 8,000. After 5 years, you want to have an 8,000. So that's your future value. Now you're just trying to find out how much should you be depositing each year. Basically, you're trying to find out what is the cash flow. All right. What is the cash flow? So here should I put future. So this is the formula for future value over an annuity due. Okay. This is the formula for the future value of an annuity due. CF is the cash flow. This is what we're trying to solve for. Okay. R is the discount rate. N is the time, the periods, or even the number of payments. Yes. So in this question, we already have our future value. It's 8,000. Okay. We already have our discount rate, 9%. As you can see, where there's zero point 0.9, that's where there's 9%. Okay. We already have the time, 5 years. Okay. So how you can solve this question? Okay. You can One easy way to solve it is like this. Okay. You just simplify the expression until you're able to find the value of the cash flow. So we start again here in the brackets here. 1 plus 0.09, 1.09. Okay. 1.09 to the power 5 minus 1 divided by 0.09. Okay. Even this 1 plus r right here, I've already added 1 plus 0 0.9. Okay. Simplifying it just step by step. Then 1.09 to the power 5 is 1.5386. Okay. The 1.5386 minus 1 is 0.5386. Okay. Then 0.5386 divided by 0.09, what we get 5.985. Okay. Yeah. This 1.09, this thing was just left it as it is. Mhm. Then now we say 5.985 times 1.09, 6.52. Okay, so now in order to get the cash flow, we divide both sides by 6.52, right? So 8,000 divided by 6.52, you get 1,226.99. Okay. So this is how much you need to be depositing each year for 5 years, and you have an 8,000. Okay. Any questions? Okay. So yes, here the secret is just remembering the formula for these annuities. But see, if the annual interest rate is 10%, how long would you have to wait before a 17,500 investment, excuse me, at least doubles in value? Give the minimum number of years required. Okay. Annual. Mhm. No, it's the time. Yes, here yes, you can use it to the future value or present value formula. Either formula will work. Yes, because the original, these are the here. Remember, present value equals future value 1 plus the rate to the power negative t. And then future value equals present value 1 plus r to the power positive t. Okay. Yeah. So you can use either, but preferably you would want to use this one with a yes, yes. Okay. Now there's also another trick you can use, but this one I don't think this one just for your general knowledge. Okay. This is called Rule 72. Rule 72 tells you how long it takes for an investment to double. Okay. And it just says time equals 72 divided by the rate. Okay. 72 divided by the rate. Okay. The rate is 10%. So it says 72 divided by 10, 7.2 years. Mm. As if you can just find out how long it will take your investment to dump. Um, then this formula here, let me show you how it was derived. This one here. Okay, it's from the same. This is from this one here. Future value equals present value 1 plus r to the power t, or to the power n, since you use it to the power n. So you're just trying to make n the subject of the formula. Okay. So in order to make, so it's better you know it like this, because to remember the to remember where is this formula. Yes, this we're coming down to this, but it might be hard for you to remember it just like this. So you need to remember how it comes down to this. Okay. So first things first, divide both sides by the present value. Okay. You're going to have future value over present value equals 1 plus r to the power n. So this exponent, we need to bring it down. Okay, we need to remove it from being an exponent so that we can find the value of n. So the way we can do that is to introduce logarithms. Okay, so you're going to say log fv over pv, and here you say log of input like this, step by step, so that so you're going to say fv over pv equals, so you're going to bring in the logarithm. So you're going to say log fv over pv, then you're going to say n log 1 plus r. Okay, this n, by bringing in the logs, the n has come down here. Listen. And if you want to make n the subject of the formula, you divide both sides by the log. So you get rid of this. Okay, get. So have you seen n equals log fv over pv over log 1 plus r, which is this one here. Log fv over pv over log 1 plus r. Okay. So if we use that formula, the future value is 35,000 because we want our investment to double, right? So, so 17,500 times 2 is 35,000. 2 times 17,500. You get 35,000. This is how much you want your money to be. It has to dump. So you can say n equals log 35,000 divided by 17,500 divided by log 1.1. Remember, the r is 0.1 here. Okay. Yes. So 1 plus 0.1, 1.1. 35,000 divided by 17.5, that's log 2. Okay. That is log 2 divided by log 1.1. So on your calculator, you just type in log 2, you get 0.693147. And you type in log 1.1, you get 0.0953. You divide the two, you get 7.27. Any questions?